Hello everyone, I am Prashant Bhatt. I am pleased to present our paper Task Agnostic Representation Consolidation, a self-supervised based continual learning approach. Continual learning refers to a training paradigm where deep neural network is trained on multiple sequential tasks. However, training sequentially on multiple datasets violates the IID assumption. Therefore, the learning objective for the current task enforces large weight changes, leading to catastrophic forgetting of older tasks and overfitting on the current task. Catastrophic forgetting leads to drop in performance. In the worst case, the older task is completely forgotten. There are three broad categories of continual learning methods that partially address catastrophic forgetting. Weight regularization methods estimate the parameter importance and impose a penalty on the weight changes. Parameter isolation methods allocate distinct set of parameters for each task. The rehearsal-based methods, they make use of a memory buffer and explicitly store raw examples with their ground truth labels. During subsequent tasks, these stored samples are interleaved with the current task samples. Given sufficient buffer size, the rehearsal-based methods have been quite successful in mitigating catastrophic forgetting. Experience rehearsal methods rely on task-specific learning to amass knowledge about previous tasks. Task-specific learning with cross-entropy as an objective comes with several problems, including lack of robustness, the possibility of poor margins, prior information loss, and the representations of the observed tasks drift when new tasks appear in the incoming data. The problems directly or indirectly impact catastrophic forgetting in continual learning. We assume that task-specific learning is the root cause of these problems and is not well equipped to deal with catastrophic forgetting. Therefore, task-agnostic learning in addition to task-specific learning might hold the key to further mitigate catastrophic forgetting in continual learning. When we say task-agnostic learning, the first thing that comes to our mind is self-supervised pre-training. The pre-training prior to continual learning training comes with its own challenges, namely non-availability of the pre-training data. Even if available, the data distribution of the future tasks is not known beforehand, leading to a domain shift. Computational costs and longer task sequences diminish the effect of self-supervised pre-training. One of the ways to circumvent these problems is by integrating the SSL algorithm into the continual learning training itself. Therefore, we propose our method, task agnostic representation consolidation, which integrates task agnostic learning into continual learning training, thereby addressing these aforementioned problems. Task agnostic representation consolidation. Our method consists of a common backbone and three different heads. Each of them correspond to SSL, classification, and rotation prediction. The training is divided into task agnostic phase and task specific phase. During task agnostic phase, TARC learns generalizable, robust, and transferable features through SSL objective. In our case, we use supervised contrastive loss, but any SSL loss can be used instead. During task-specific learning phase, the model is fine-tuned using labels using the classification head. However, as we show later, the task-agnostic features will be overwritten by task-specific learning, bringing us back to square one. Therefore, we employ an auxiliary loss to preserve the generalizable features learned in the task-agnostic phase, thereby leading to a significant improvement over experience rehearsal baseline. We choose rotation prediction as an auxiliary task for its simplicity, limited computational overhead, and similarity to classification. In addition, rotation as an augmentation does not change the underlying semantics of the input and does not need any additional forward passes through the continual learning model. The algorithm of our method can be seen on the right. Due to its simplicity, TARC can be used as a framework on top of existing state-of-the-art methods. We extend one experience rehearsal method and two regularization based methods with TARC and show discernible improvement over the respective baselines. Here we provide an overview of the working of each component in our method. As can be seen, neither auxiliary task nor task agnostic learning is better equipped to deal with catastrophic forgetting on its own. However, when they are coupled together, they perform better than ER. It's clear that both task agnostic learning and auxiliary loss are critical for our method, since the former helps in learning generalizable features, while the latter reduces the risk of these features being overwritten from the task specific learning. The task agnostic learning and the auxiliary loss complement each other when coupled together in our method. Here we present the top 1 accuracy of different methods with and without TARC. As can be seen, TARC shows a strong performance in majority of the benchmarks, especially when the buffer size is small. We argue that our method is able to retain information more efficiently than ER by learning task agnostic representations. In case of a larger buffer size, our method is behind ER only by a small margin on smaller datasets. Due to high class to buffer ratio, tiny ImageNet dataset is one of the hardest benchmarks under class incremental learning. Our method outperforms baseline across all buffer sizes in tiny ImageNet dataset. The relative improvement compared to the baseline improves with the increase in image size. The task agnostic learning is able to discriminate better for STL10 and tiny ImageNet when the images are comparatively larger in size. To prove the generalizability of our method, we adapt two regularization based methods, namely online EWC and synaptic intelligence, and provide the results in domain incremental learning and general incremental learning scenarios. We also do not use any replay for these methods. In both of these scenarios, TARC outperforms the baselines by a large margin, indicating that our framework works across different continual learning approaches. In addition to the main results, we also present forward transfer as the difference between accuracy just before starting training on a given task and the one of a randomly initialized network. As is the case with rotated MNIST, it requires the continual learning model to classify all digits for 20 subsequent tasks, with images rotated by a random angle in the interval between 0 and 180. Therefore, the positive forward transfer is not only plausible, but also highly desirable property in this setting. As far as backward transfer is concerned, we compute the difference between the current accuracy and its best value for each task. As can be seen, TARC exhibits strong forward transfer and improved backward transfer when compared to the respective baselines. Autonomous continual learning agents operating in the real world are exposed to ever-changing environments, often influenced by illumination and weather changes. Therefore, it's pertinent for continual learning agents to be robust to data distributions with natural corruptions. In this analysis, we evaluate our method against common image corruptions using CIFAR-10C. The shaded region in each bar is in the following figure indicates an improvement over the baseline. Our method has lower mean corruption error across all different corruptions. Evidently, task agnostic learning, when coupled with task specific learning, brings discernible benefits in terms of robustness to natural corruptions. We also extend the ablation study with more combinations of pre-training, auxiliary loss, and TARC. In line with our understanding, task agnostic learning and auxiliary loss complement each other when coupled together. Our method is computationally less expensive and superior to pre-training on tiny ImageNet. As number of tasks increases, pre-training has little to no effect on different continual learning methods. On the contrary, TARC provides discernible performance improvement over all other combinations with or without pre-training. We argue that this performance improvement over the pre-training is essentially due to our method's ability to diminish domain shift. Similar to our method, remembering for the right reasons, RRR proposed a training paradigm that is extensible to existing continual learning approaches. The figure presents comparison of RRR against our method on CIFAR 100 under different number of task sequences. As the length of task sequence increases, our method clearly outperforms both RRR and ER baseline. Our method is able to consolidate generalizable features better and mitigate the effect of catastrophic forgetting. Unlike pre-training, the effect of task-agnostic learning does not diminish with longer task sequences. Since both TARC and RRR are generic frameworks, a combination of them might improve our proposed method even further. In this work, we proposed a novel two-stage continual learning paradigm that intertwines task-agnostic and task-specific learning. Unlike self-supervised pre-training, our method does not suffer from domain shift, non-availability of pre-training data, and additional computational costs. Furthermore, the effect of task-agnostic learning in our method does not diminish with longer task sequences. Our method can be easily added to memory or regularization based approaches with consistent performance gain across more challenging continual learning settings. Extending our method to algorithms oblivious of task boundaries and or knowledge distillation approaches are some of the useful future research directions for this work. Thank you for listening. In case of any questions, please write to us to the email addresses mentioned on the screen.